So for our next sample problem, it says here water is being heated in a closed pan on the top of a range while being steered by a paddle wheel. During the process, 30 kilojoules of heat is transferred to the water and 5 kilojoules of heat is lost to the surrounding air. The paddle wheel works amount to 500 Newton meter. Okay, so here is our illustration of the problem. We have a water inside the container, or it says closed pan. We can draw if you, or you can draw if you like, a pan, frying pan, then maybe a stove, and here's the heat source. Then we'll put the cover. Then we do some mixing here, a ladle or whatever. But anyway, that I think this is more a larger scale process approach. So I think this is more appropriate, or just my preference, right? So it says here that during the process, it's a heating process, which means we have a heat source here that heat is added to the system, to the water. And it says that 30 kJ of heat is transferred to the water. And because through time, the temperature is higher, the temperature of this container, because the water is actually higher compared to the temperature of the surrounding air, then that is why there is heat losses. So heat is transferred, 5 kilojoules of heat is lost to the surrounding air. So there's a transfer of heat to the surroundings, and that is a heat loss. And since we also do mixing, then that means that there's an energy input as well. So paddle wheel works amount to 500 Newton meter. So you see here, it uses this unit of Newton meter, but it must not be confused with the moment in mechanics. Although in mechanics, the moment is for SI units, it's also in Newton meter, but it's never in joules. Now this one for in thermodynamics, when we say Newton meter, we can translate that into joules, right? So moving on. So first step, as usual, is to draw the analysis, right? So solution first, here, solution. Then step 1 is to draw the analysis. So when I say draw the analysis, specify the system. So here's our system, and let's say it's water. Then if we specify the system already, then draw the boundaries, and then draw the interactions. Okay, now the question is it really the water that that's our system? Is it the water? Is it the container plus water, or is it the paddle wheel? So all right, so maybe you can figure that out, but I think sometimes the highlight from the highlight or highlighted let's say terms here, let's say water, right? So if it's all about water and we have the properties of water, then I think that's a hint already, right? So water is our system in this problem. All right, so next is specify the interactions. So we have heat source. That means that we have heat input. So Q input is equal to 30 kilojoules of heat, right? So this is 30 kilojoules of heat. And then we have heat losses, right? Heat loss amounting to, I think, 5 kilojoules of heat. And then work input from the paddle wheel. So a work input of 500. So work is so we have work input here. So work is 500 Newton meter. Okay, so the units here is for heat. It uses kilojoules, so 1,000 joules, and Newton meter is just equivalent to joules only. So in order to be uniform, then maybe we can just write here this is equal to 0.5 kilojoules, right? So we can use that so that we can have a uniform units, right? So what else? Then we need to specify the states at state 1 and state 2. So what are the properties? Let's see. So the paddle wheel works, right? So I think it's incomplete. So determine. I think we have to find determine the change in internal energy of the system, right? So, right, so no specific data regarding a U1 or U2 or kinetic energy. So I think assumptions here for additional informations. Delta KE is 0, and delta PE is also 0. But the delta U, although it's not given here, but actually that's what we're looking for. So although we don't have specifically the value at state 1 and 2, but the delta U, there must be a change in the internal energy because we are in this heating process, and therefore the temperature, whatever the initial temperature of this water is, after some heating process, the temperature will increase more, or it might be reaching its change of phase. So there must be a change in the internal energy, right? So delta U is not equal to 0, right? So there is a change in the internal energy. Right, so now that we have drawn the analysis, then now let's apply. Right, so apply the energy equation. So what form? Is it the total form? Is it the rate form? Or is it the specific form? Right, so here from the units, we can see that it's in its total form. So let's write the total form. So energy in, right, summation of energy in minus summation of energy out is equal to the change of the energy in the system, right? And the left side corresponds to the interactions, and the right side corresponds to the delta U, delta K, delta P. Right, so energy is going in. What are those? It's this one, the 30 kilojoules of heat input, and the 0.5 kilojoules of work input. So let's write here 30, or first is Q in plus work input, right? Minus what's the energy that's going out? It's the 5 kilojoules, so Q out. So Q out is equal to the change in the energy of the system, delta U plus, right, delta PE plus delta KE, wherein this one is just 0. So to simplify, we have Q in plus work in minus Q out is equal to delta U. Right, so substitute the values. We have 30 plus 5, 30 plus 0.5, right, 0.5 kilojoules minus what's the out? It's 5 kilojoules. So minus 5 is equal to delta U. So delta U now here is, I think, 25.5 kilojoules, right? So that's just how simple it is to apply this energy equation for energy analysis. Right, so again, first is draw the analysis. Make sure that you have selected the best system for analysis, and also draw the boundaries and the interactions. Specify, write the important informations or the given informations, and do some assumptions. Especially if there's no given velocity or there's no change in height, then you can assume that they are 0. Okay, and then apply the energy equations, and then that's it. Okay, so next sample problem, it says here a vertical piston cylinder device contains water and is being heated on top of a range. During the process, 65 BTU, that's in English units, British thermal units for heat. So 65 BTU of heat is transferred to the water, and heat losses from the walls amounting to 8 BTU. The piston rises as a result of evaporation, and 5 BTU of work is done by the vapor. Determine the change in the internal energy of for this process. So here's our figure here, illustration. So we have a piston cylinder device. Now, when we say piston cylinder device, it's not just limited to the internal combustion engines, although it's also a piston cylinder device. But the idea or the concept of this, that we have this moving cover here. So example, the water is inside, and we have this cover on top, but it is free to move. Of course, we assume that there's no mass loss in this along this side, of course. Right, so it's just free to move so that we can achieve a constant pressure process. Right, so it's you just have to extend that concept. So it says here that 65 BD of heat is transferred to the water. So there's heat input to the water, and because it's a heating process, then this container will eventually have an increased temperature, and the temperature of the surrounding air is less than the temperature of the container. That means there's going to be a heat loss, a heat that's going out. So the amount is 8 BTU. Okay, so additional information here says that the piston rises as a result of evaporations. So that means that after some time, some portion of the water is evaporated. It becomes vapor. So it's a different phase. And because it's a vapor, there's going to be an expansion, or it has these characteristics to expand. So because of that expansion of vapor, then it will push this piston upward. All right, so that's the idea of this problem. Right, so now for the solution. So step one, as usual, is draw the analysis. Okay, or what else? Draw the analysis. So maybe we need to draw two figures here. So one is the analysis is that here's our initial state, right? And we have this piston right here, but then the final state, because some portion of the water is evaporated, then there's a movement of the piston. So right here, so first is it's just liquid, but here we have already vapors. So let's write here. This is water. Let's say liquid water, and this is vapor, and this one is just liquid. Right. So for this state, okay, so now let's specify the boundaries. I think the best one to choose is maybe not that one, or maybe we need to draw, or let's just write initial state, and this one is the final state. Right, so including expansion, or includes expansion of vapor. Okay, so next is we'll select this event. So the drawing of your system. Now, what is the system? Is it the piston, the cylinder, or is it the piston plus cylinder, or is it just the water? So again, this is just water. Right, so we'll choose water because anyway we are there's not much data about the containers, so commonly it's the substance. Right, so now the interactions. So we have heat input of 65 BTU. So heat input of use Q is equal to 65 BTU, and then heat output of 8 BTU. Right, so heat output of 8 BTU. Okay, the next is the work output. So there is expansion. So recall that in topic, I think topic 6, we have discussed the different types of expansion. Different types of work transfers. So one is the expansion work, because the substance. When we say expansion or contraction, usually we are referring to the substance that is compressible, so which includes gases and vapors. So because of expansion, the gas or the vapor will push this piston. So it's gonna be work done by the system. So work of what's the amount? 5 BTU. Right. So 5 BTU. Okay, so once everything is set, then I think we can now now write or okay, apply the energy equation. Right? Energy equation. So, what form? Is it the total form, rate form, or is it the specific form? So we can just use the total form because the units here are in total form. Okay, so energy in. So summation of energy in minus summation of energy out is equal to the change of the energy in the system. Now, what are the energies that's entering or leaving? So we have Q in here, right? So Q input minus we have an output of work and heat. So let's just say Q out plus work is equal to the change in the energy of the system, which is just simply delta U. So there's a change in the internal energy. Now, by the way, the system is water. That does not just include the liquid, but rather it includes both the liquid and the vapor, because it's a closed cylinder, right? So that also includes the vapor, and it's still a pure substance because whether it's in liquid or in vapor, the chemical um, chemical form is still the same. So it's still H2O, H2O. So that includes vapor as well, right? Water, or maybe we'll write here water plus vapor. Right, so now let's substitute the values. So Q in is 65 minus 8. Q out is 8. Okay, plus the work output of 5. So this is equal to delta U. So 65 plus, 65 minus 5. So we have 60, we have 52. So delta U is equal to 52 BTU. Right, so that's just how simple it is. For some of the problems, actually, the problem or the challenge for analysis, energy analysis, is actually on how to find the properties. Because later on, maybe in next week topic, you have to find the properties. So at this point, we're just skimming the surface, right? So next sample problem. Now we'll do an open type problem. Say here a fan that consumes 20 watts of electric power when operating discharges air from a ventilated room at a rate of 1.0 kilograms per second. Determine the discharge velocity. And we have these assumptions here. Right, so actually this problem is taken from one of our reference texts, the latest edition by Senchel et al. 2024, copyright date 2024. We have that. We have a hard copy for that. The problem actually is different, and so I just tried to tweak it and also add these assumptions because, of course, when we do analysis, it actually requires knowledge on some other subjects or courses like fluid mechanics. So I just give this plain right to you. So the assumptions, I have still air at room. Okay, so the problem here, it says we have a fan that consumes 20 watts of electric power. So here's our fan installed in a room. So let's say maybe an exhaust fan. So that exhaust fan is actually for the transport of air. So fans is one of the fluid machines for the transfer of air. So fans, blowers, and compressors, they're all related to each other. They're not exactly the same, but they are related to each other. They are fluid machines for transporting vapors or gases. So it says here that it consumes 20 watts. 20 watts of electric power. Of course, in order for this blade to rotate, then you have to have you need to connect it to an electrical source. And when it is operating, then it discharges air from a ventilated room. So from a ventilated room at a rate of 1.0 kilogram per second. Right. So I think I need to discuss this more. In a more detail. So here's our fan. Right, and that fan has a blade here. So we need to connect this to an electrical source so that we can have an input power, right? So input power from, let's say, from an electrical source, so that it can rotate this shaft. So once this shaft is rotated, then the blades connected to this shaft is also rotated. So what will happen is, let's say we'll detail this blade here. So let's say we have a shaft and maybe we have a hub and the blades. So the blade is actually the ones hitting the air. So to increase the energy or to move it or to propel it. So it's actually the work done by this, maybe we can say work done from this rotation. The work is transferred, or the energy is transferred to the moving air by heating that air with this fan blades. So in that way, it maybe increases the velocity or maybe increase the pressure or whatsoever, right? So that's the idea about this fluid machines, right? So it's installed here so that there's going to be movement of air from the inside room to the outside room. Okay, so what else? Then the only data that's given is this, to the 20 watts. So that means if we choose air as our system, then this 20 watts of electricity is just the same as this. All right, so 20 watts of electricity is just the same as 20 watts here, because we don't. I mean, that's the only information that we have. We don't have any efficiencies like the brake horsepower or air horsepower. So there's not much data. So if we choose air as our system, then that means the electrical input here is just it's going to be the same here. Okay, so what else? Then compare. Actually, you can also feel that if you, I mean, at the back of the fan, there's not much velocity here. You don't feel much much velocity here compared to if you are standing right in front of the fan. Because if you're, well, let me draw it here. So let's say we have a stand fan. So it's blowing air right this way. So if you are here, you can actually feel a lot of velocity, but if you're here, you don't feel much velocity, right? So there's actually a difference in the velocity. Now, if we consider an entire room, then probably we can say, or we can assume that the velocity in the room is so still air. So that means that the velocity is equal to 0. So we can assume that, or approximately equal to 0, unless we have information about it. But since there's no information, then we can just safely assume that it's just equal to 0. Okay, what else? The kinetic energy. The potential energy. So did that fan change location after the process? Of course not. So therefore, there is no change in potential energy as well. Okay, next one is the temperature. Did the temperature of the air that passes the fan increases? Did the temperature of the air increase? Maybe yes. Maybe in reality, maybe we can say yes, because any electric motor actually after some time, it there's a heat loss here. But since there's no data given about the heat losses, so can we assume that there's no change in the internal energy or the temperature of the air? So that's those are the questions that we can include in the analysis. Right. So now let's move on to the analysis. Right. So for the solution, so first is, let's draw the analysis. So first is select the system. What is the system? Is it the air or is it the device? So actually, I have tried computing using the air or using the device, and I just arrived with the same answer. Now I think the best approach would be to use the fan as our system, right? So let's try here. So let's say here's our fan. Actually, the substance is air. The substance is what's going in and out. But anyway, I'll use the fan. So that's our system. Then specify the boundaries. Right, and we have movement of air here. So we have air moving. And the data is m is equal to the mass flow rate of 1.0 kilograms per second. So this is 1.0 kilograms per second. That's let's say a mass flow rate. Right. So the interactions, for the interactions, we don't have any heat loss, or heat input. So the only input is the work, the electrical work. So here's our work input. Right, so we have to use our notation, our special notation for this. Right, so work is equal to 20 watts. Okay, next, what are the energies, or what other energies crosses the boundary? We have a moving mass, so that means we have a mass flow or energy transfer via mass. So we have F in, and we also have F out. Right, so F in and F out, going in and going out. Okay, so what else? For the assumptions, other assumptions, so delta KE is equal to 0, delta P, sorry, this is not 0, the no change in temperature. There's no change in temperature. Right, or I think I have included here, no change in enthalpy. So recall that enthalpy is it's U plus BV, right? So the no change in enthalpy. No, I think there should be no change in internal energy. So it's not the enthalpy of the air. It's actually the internal energy. Right. So internal energy. So it's not the enthalpy because we have change in U plus PV. I think this is correct. So sorry about that. It should be enthalpy because H is equal to U plus PV. This is internal energy related to temperature. Yes, we can say that this is 0. The pressure and the volume, actually the volume is the same. So since we have the same cross-sectional area, I think this is the same. The pressure is the same. So for fans, there's not much pressure difference. So we can say that the pressure here is the same because the pressure of the air here at the inside side, let's say atmospheric pressure, so it's the same as the outside air, the pressure here at the outside air. So yes, this is 0. This is also 0. So I think we can say that the enthalpy of the air is, or the change. No, I'm not saying that the enthalpy is 0, but rather the change in the enthalpy is 0. Right, so let me clear that. So delta H is equal to 0. It's not H only. So H1, there is enthalpy of the air, but the change in the enthalpy is what we are saying as 0.